I am going to show you how to teach a second grader something that I couldn't do 10 years after I'd gotten my graduate degree in physics. Math is all about how we look at things and patterns. If one looks closely at the picture, we can see a young woman looking over to the left with the dark hair on the side. But if we look at these two and see them as eyes, and this is a nose and this is a chin, we see an old woman with dark hair over her forehead, also looking to the left but downward. Sometimes we have physical limitations that keep us from learning things. For example, some people are colorblind. So we might be able to understand why some people take longer to see things than others because of how they look at things and limitations that they must overcome. So let's begin. We start off with the Pascal triangle, which on the top row has 1 as the first column and zeros in every column after. We also notice the overall structure of the Pascal triangle. In the first column, we have all ones. And the rule to obtain the elements in between is to take the element above and the one to the left and add them together. So 3 plus 3 is 6, 1 plus 0 is 1. We now look at factorials. In factorials, a number with an exclamation mark means that number multiplied by each number, preceding number, until we get down to 1. So 4 factorial would be 4 times 3 times 2, 1, which would be equal to 24. We can also prove that 0 factorial is equal to 1. If we want to now calculate a factorial expression, we replace the 4 factorial by 24 and the 2 factorials by 2, and we'd find 24 divided by 4 is equal to 6. This is the key to the problem in terms of using the factorials judiciously. We've now shown a series of calculations with factorials for the 2's and the 4's. And we then proceed to replace them by those factorial numbers. This one you'll remember we had calculated on the previous page. The other part that is important is layout. All we're going to do is now change the orientation and our rows become columns. When we do this, a pattern jumps out that the last number in our factorials start off from 0 and go up to the number in the numerator. We see this in each column. We also notice that when we add the factorial numbers in the numerators, they add up to the number in the denominator. So in the case of the 3's, 3 plus 0, 2 plus 1, 1 plus 2, and 0 plus 3 all add up to 3. We now need one more step. We take a series of a plus b's added to each other, increasing it by 1 for each column. We then place the factorial coefficients in front of each of these numbers, noting that a 1 is assumed we see no number in front of it. We then take and write these in the vertical format. And we replace those numbers in the Pascal triangle by their factorial equivalents. We now take and place an exponents on each of these ABs. Noticing the exponents follow the same pattern as do the factorials, and also adding up to the numerator. You will have to accept this, trust me on this, that these things are equivalent to a plus b to the second power, a plus b to the fourth power, and so on. We now take those, and you'll remember that there was a 4 factorial here and a 3 factorial. We divided those into the exponents in the answer. Now we're just going to take that and repeat it on the next page, except we're going to put e to the b multiplied by e to the a above that. And it turns out that we can see a pattern here, that each of the numbers in the infinite series are b raised to a power divided by the factorial equivalent of that power. And now we use the distributive property to multiply these out, which would result in this as an answer. And you already trusted us on this, but now what we notice that this pattern here is the same as the pattern for e to the b, except wherever we saw a b, we have an a plus b. So we just replace that by a plus b, and we get e to the b times e to the a is equal to e to the a plus b. That's all there is to it. You only had to trust me on one thing. But these are what the missing pieces are, which could be taught to a first grader, second grader, but are more appropriate to higher grades. Here we have the binomial expansion, which is basically the algebraic application of the distributive property where we substitute numbers instead of letters. We had to multiply fractions in there. The simple rule for fractions was multiplying numerators and denominators. And for exponents, when we multiply exponents with the same base, we can see from this proof that we add the exponents, where a to the second is a times a, and a to the third is a times a times a. The only step missing, and this was something I was not taught in school, was how to prove the rule for the Pascal triangle. And now you have the complete problem. Thank you for helping make a second grader smarter than me.